Welcome to the session on scalability. This will be presenting Jason and I from Adaptive, and then we have our a use case from McGill University. Thank you. Sorry, I forgot. Got to put all these things on the slide because I forget everything. We'll dive right in. All right. Obviously, one of the main focuses of our product development recently has been scalability. We have currently a customer we're trying to sell to that has 10,000 nodes, and we know in the future we're looking at that's going to just keep growing and growing. Some people are writing papers about 100,000 node clusters, and just these things just continue to grow and continue to grow. So we're looking at large numbers of jobs, large numbers of nodes. Other sites that maybe don't have as many nodes, maybe they have a lot of smaller nodes, but they're pushing through. Some sites are telling us they want to run 100,000 jobs a day. Some sites want to run more. So these are the scalability considerations we're looking at and we're orienting our development towards. This is just the scale we're looking at in terms of growth and where the future of HPC and clusters are headed. So for Torque, we have a few different ways that we approach this. We focus primarily on the number of nodes and the number of jobs. Torque 4.0 addresses a lot of these needs, although there's still some future considerations that we'll continue to work on. Did I skip something? Okay, sorry. All right, when we're looking at the number of nodes, one of the main considerations is startup. It's actually easier to have all the nodes in a stable state than it is to have them all on startup, because at startup, every mom has to talk to the server to say, I'm here. And so there's several different ways to approach this. First of all, this is vastly improved in 4.0 with multi-threading the server. Obviously, it's able to handle a lot more connections at once. In 4.01, we actually also fixed a bug of how we're handling the incoming connections. So you see those market improvements. But there's additional parameters to help control this. One of the options is to start your PBS moms with a -W. This is just telling the mom to wait. This basically takes advantage of the mom hierarchy on startup. You're telling the moms, wait until the server tells you what your hierarchy and what your contact path to the server is, and then once you get that, follow your contact path. This reduces the need, it obviates the need for every mom to talk directly to the server, because if the mom's reporting through the hierarchy, it'll just report its startup through the hierarchy, and it will just sit there idle until the server contacts it and says, here's your mom hierarchy file. Referring to the mom hierarchy, if you're running a default system, you get updates every 45 seconds. If you have 10,000 nodes, you're looking at 222 requests per second just to maintain a stable state. If you're looking at 100,000 nodes, you just multiply that by 10, you get over 2K requests per second just to hold a stable state. That's without running jobs. Larger sites often find it's necessary to set this to a higher interval, maybe 120 seconds, maybe 5 minutes. It depends on basically how often things are changing in your cluster. If you're running a very large system and you have jobs that only finish every, if your jobs run for days, you probably don't need an update every 45 seconds from the mom. If you're running jobs that are going to run for days, or so these are parameters you can play with. You can also take advantage of the mom hierarchy file. That's a new feature in 4.0. I'm not doing a complete coverage of it here, but basically just allows you to set up a file, and you say, we would like our moms to report through this path to the PBS server instead of directly contacting the server. There's a lot of things you can do to take advantage of this. If you adjust your router settings and give priorities to the moms that report on other moms, then you can even speed up that process more and just make it even faster for you to get your reporting done, get that overhead out of the way. And the idea of the mom hierarchy was that people would make it to match their network layout. So nodes that are close to switches, or nodes that are all on the same switch, maybe pass to the node closest to the switch, and that node passes it across the switch. That's sort of what we're hoping people will do with it and that's what you would do with it in order to get the best usage out of, in terms of reporting this larger number of nodes. Another very similar problem is when you have very large jobs. Some of the people one of our sites has a 3200 node cluster, and they sometimes run 3200 node jobs. If you have one single mother superior daemon that's trying to handle all these requests, it pretty much takes that node out of the job, and it also, it's just not well equipped to stay in contact with thousands of other nodes. Job Radix sets up a tree for this reporting, which reduces the stress in a very similar way to the MOM hierarchy file, in that it allows them to contact through the tree structure. You can set how many nodes you want each node in the tree to talk to, so you can set it to, you can set it to 2 or 3, and if you just setting it to 2 or 3 takes away a ton of the stress. This just reduces that stress. You don't have that single point of failure. You're not going to have as many packets dropped because you have 3,200 nodes trying to contact the same point in the network at once. It reduces a lot of unnecessary job failures due to just network latency caused by a model with a single stress point. Other miscellaneous scalability help in 4.0 that kind of help everywhere. Job, node, and queue access now happen in constant time instead of order n. We've switched these to be resizable arrays with an accompanying, well, basically they're lists, but we have a hash table that tells it the index in the list. The list so that we can maintain the order, because obviously, it makes a certain amount of sense to have your jobs report in the order they're submitted in a queue stat or in a show queue or whatever. But we also want to access them quicker. In all versions prior to 4.0, if you had 100,000 jobs, you could have done a queue stat on one specific job or a queue run, or Moab could be trying to run a job, and it iterates over all the jobs to find that one. So you're looking at order n. And as you get to very large numbers of jobs, if you have 100,000 jobs, this is a painful transaction. So change to order n. Running a job used to go over every node up to 5 times when it looked at how do I run this job. And this is even with Moab submitting it and saying go to these specific hosts. It could still look at every node up to 5 times. This is now reduced to 1, and if you have the names, it goes directly to them. So it can be as low as a constant time interaction, but it's at worst n. So this is a lot faster. And then obviously the nature of making it multi-threaded allows the server to handle a lot more requests, process obits in parallel, process a job obit at the same time that it's processing a run job request, at the same time that it's processing QStat. You don't get the blocking problem that you had. And again, if you're running a smaller site, you don't notice these, but as we go to bigger and bigger, if you have 100,000 jobs in the queue, it can take the server, it could take up to maybe a minute for the server to do all that processing. During that minute, it's not doing any request handling. Everything's building up. You're getting, you may be getting network timeouts as a result of slowness in response, things like that. A lot of that just goes away or is significantly decreased by making it multi-threaded. Jason's going to talk about a lot more of the Moab considerations, so I'll pass the time over to him.
All right, so those of you who don't know me, I'm Jason Booth. I work on the support team as a technical account manager, and that's a fancy name for just having a bunch of clients that I'm responsible for and report to. So without any further ado, Moab considerations. So with scalability as it relates to Moab, I broke it down into 2 sections. One, you have job scalability, and the other is node scalability. With job scalability, there are a bunch of parameters that you can fine-tune to your environment so that the system can scale and be more responsive as you move into those large number of jobs, be it 10,000 to 100,000 or more. So with that, the first parameter, job aggregation time, can be set. Basically what this does is when a job is submitted into, say, Torque, Torque notifies Moab that it has a new job to run. Moab then immediately kicks off a scheduling cycle. Well, this isn't very efficient when you're talking about submitting hundreds of thousands of jobs all at once, because what that would do is kick off a new scheduling cycle for each job that went in. So this one just tells Moab to evaluate all the jobs as one big group. Next one is limited job CP. So setting this to true will cause Moab to load all non-completed jobs from the checkpoint file, regardless if their resource manager is responsive or not. What that can do, that can speed up startup time, and responsiveness from Moab. All right. With that too, you also have the RMCFG async start. That one will kick off a job optimistically inside of Moab. With that, you may want to consider async delete as well if a lot of your users end up deleting those jobs sometime during that period. Okay, so next parameter, we have another RMCFG parameter, job RSV create. So in older resource managers, what they would do is they would change the resources that were allocated to a job. In newer resource managers, that's not the case. Moab, in order to work better with this, used to destroy reservation and then reapply reservation each scheduling iteration. By setting this, it tells Moab to not do that, so you increase its performance so it doesn't have to evaluate all those reservations. So you can also optimize your backfill too. If you set the optimized backfill, if you have a system reservation in place, you'll see significant improvement performance on your cluster. So it won't continually evaluate those jobs that could potentially be backfilled. Another consideration too is to set your log level. Within large clusters, we recommend log level 0, log level 1. On some of our larger sites, it's common to run log level 3, but we recommend 0 or 1 when you have large sites. All right. Another consideration too is to set your job max preemption iteration. And that one will just need to be tuned according to your environment. You may have 30 jobs that you may be evaluating, or 100. You may want to, you'll have to play around with that to get a feel of what works for you. All right, for large node consideration, you can increase your RM pull interval. I've seen some sites that set it up 2-3 minutes and even larger. The default is set to 30 seconds. So again, you want to play with that with your site to see what best fits your needs. That could be helpful if you're running a very large, long job. You can set that RM pull interval to a very large time. All right. Another setting you can do is the limited node CP. And what that does is limits what information is being checkpointed for each node. That, as long as Moab's not churning through all that extra data, again, you're going to have a performance increase. And as always, consider your hardware too with large systems. We have a minimum recommendation of 8 gigabytes of RAM and 100 gigabytes of disk space. So keep in mind, the larger your cluster is, the more beefy your hardware is going to be. And now, without further ado, I'll turn the time over to Bryan Caron. He's from Compute Canada, and he's going to talk about his use case at McGill University.
Okay, thank you. So thanks, Jason. Thanks, David. So just go through and give an example of how we implement some of the configuration for Moab and Torque, of course, at our environment. I'll preface this by saying this is some of our experiences that we've come across in working with our system, which I'll describe in a minute, as part of an organization called Compute Canada, Calcul Quebec, which is kind of a national HPC foundation that we have in Canada, but it's specific to our use case at McGill that we've experienced. So I'm going to talk about some of the features that things that we've done to bring about what we consider scalable for a large node count. Obviously, it's not large in some of the sense of tens of thousands of nodes. As you'll see, we're talking about, in our case right now, 1,200 nodes and doubling to approximately, going to double that later this year. But I just want to preface this with some comments to say that these are our experiences. By no means are we perfect in the way we do things, and we're certainly looking to get comments and feedback from people about what I'm talking about today to improve the overall experience how we operate the facility, but also how we deliver it as a service to our users. So I'll just jumped ahead here. The outline of my presentation, I have an abbreviated version, so I'll keep it short so everyone can have discussion. I'll give you a highlight of what the actual infrastructure is that we have in place at McGill in terms of our resources that we call Gilman. Then I'll talk about some of the aspects. I'll touch on some of the features that Jason and David talked about already, but this is in the context of Moab 6, so some of all the things that were discussed there don't necessarily translate. But I'll talk about the areas of how we do allocation management, how we manage the resources in terms of various limitations that we put in place that we've so far found have worked pretty well with our base of users. I'll kind of go through and very quickly summarize some of the comments that were the tunings already for large-scale systems that we've already applied, even though our system isn't necessarily in the upper echelon in terms of size. And I'll also talk about some customizations that we've done that maybe either A, we've done because of we found that certain feature sets may or may not be there in Moab, or we just necessarily don't quite understand exactly what we're doing completely yet with Moab. So again, these are just things that we've done in the interim. And I'll highlight some of the future plans that we have for the facility in terms of the scheduler, but also for the hardware. So this is Gilman, our system at McGill University in Montreal. It's about a data center, about 5,000 square feet of IT space, but we have 1,200 nodes. It's an IBM iDataplex solution that was put together and basically handed over to us in April of last year. It has 14,400 compute cores, all Intel Westmere. We also have 2 petabytes of storage online with that as part of a GPS parallel file system. And at the time, it was about number 35 in the world in June of last year. But as we know, these things are they slip very rapidly. So just in terms of the details, I won't go through all the exact details of the system, but as I mentioned already, in terms of the compute nature, we have a common x86 architecture, but in behind we have 3 types of partitions that we expose to the users, and those partitions vary in 2 fundamental ways. One, the amount of memory that we provide on a per node basis. They're effectively on a per core basis, and as well as how we interconnect the nodes in terms of the IB fabric in behind. So in terms of the different partition types that we have half the machine more targeted toward serial workloads, so it's a 2-to-1 blocking in the IB fabric side. We provide effectively 3 gigabytes of memory per core, but then we take the other half of the machine, we split it into a large memory portion, what we consider large for that type of workloads, and as well as a high bandwidth portion. Both are non-blocking in terms of IB, but then we have a segregation in terms of how much memory we provide per node. It's a fat tree network, so it's simple in that regard. But in this case, though, we obviously want to try and tailor and have people send their workloads to the appropriate locations on the system. So the 3 partitions I talk about will right now form the basis of how we organize our queuing structure, which I'll talk about in a minute. So obviously, which may be obvious to some people more than others, we're not a national lab in the sense that we target very specific use cases, but we have a very diverse set of clients and users using the system, ranging from bioinformatics, genomics, animal sciences, all the way up to the more fundamental sciences in terms of physics. We're also a Tier 2 computing center for the ATLAS experiment on the LHC experiment at CERN in Geneva. We do all these types of things, including neurological imaging. So overall, in terms of the facility as a whole, we serve about 1,000 users from about 350 different research groups that within the envelope of Compute Canada, we organize and how we arrange those users and keep track of their usage and so on. But one of the areas that we're expanding into is the use of industrial partners that we have a strong bent for HPC. So they have advantages and dependencies that will see the advantages of scalability as well in terms of our environment. And of course, we're also doing things in terms of outreach, in terms of training new people in terms of using HPC, even down to the early grade school level. Even though they might not know it's HPC, they're actually trying to use it. So enough of that. So you might say, well, how are these people, those client base, using our system? How does it relate to large scale? In our case, what we define as large. If we look at our, since basically middle of August of last year, this shows graphically the number of completed jobs per day across the system right up to about the very beginning of April. So you can see from the graphing and the markings, we've hit in some peak points over 60,000 jobs completed per day. Going through, we can argue if that's a high throughput workload or not, but for our case it is. Some of these are driven directly by the users. Some of them are done effectively by robots because we have connections to the outside world in terms of grid systems that basically push what we call pilots. So basically they inject jobs and those jobs reach out to pull workloads in. So we have a mixture of those systems depending upon the actual user in terms of what their workload is doing. But as you can see, as a function of time, the number of workloads that we're pushing through each day is growing with these large spikes at over the 45 to 60,000, depending on the burst period of activity. Oops, very sensitive clicker. In terms of number of concurrent running jobs, as I said, we have 14,400 cores. We support a variety of workloads ranging from single core, single job, all the way up to people by default without having to ask for any special permission, being able to run jobs that span 1,000 cores across the system. If they want to do larger, they have to request access so that we can input into the system. But in terms of number of concurrent jobs, you can see we're reaching over about 2,400 concurrent running jobs with ebbs and flows depending upon when we have scheduled down times. In October and November, we had some maintenance periods that we had, and as well as the end of March. Now, in terms of the queue and scheduler configuration, this pulls upon the information from David and Jason, but right now our environment, we're using Moab 6.13 and Torque 259, so it's certainly not the latest and greatest in terms of the recent releases, but it's been a major step forward for us compared to the previous version that we were running in, October of last year. And I'll touch on some of the benefits that have come from that. I'll quickly highlight some of the queue configuration issues, which I again talked about are oriented with regard to our partition structure, but we're looking to maybe possibly update that. I'll talk about some of the aspects of how we allocate resources in terms of Fairshare. Well, it's not strictly a scaling issue, but it imparts directly how we use the system for our users. I'll touch on very briefly some of the resource limit policies that we apply. Not policies, but policies. And then I'll talk about, again, very quickly, just touching on, again, some of the large system configuration, which we're well covered already. But the thing I want to also particularly talk about is some of the customizations, which, again, may or may not be features that we're using properly in Moab, but things that we found for our particular environment have come in and to be very handy. So in terms of our queuing structure, again, it's organized based upon our partition types. So we have our serial workload queue, our high bandwidth queue, large memory, and we also apply a debug queue where we have a variety of configurations where we allow jobs at the default, can allow them to run for 3 hours, but we have certain use cases where we let people run for up to 30 days. We're looking to shrink that. But the dependency of the queue provides a different set of resources, whether it's the memory per node or the interconnect from the IB fabric side. In terms of the allocation management, as I said, we use Fairshare. And that's the model by which we actually assign certain amounts of resources for aggregate usage over the course of the year, both from the national level, meaning from Compute Canada side, right down to the implementation on individual resources. So the Fairshare is the concept that underpins all of how we do this in terms of how we give resources to certain projects for researchers and how their allocations are used over the course of the year. And for that, we tie into the Moab Identity Manager interface. We basically then have an external database that has all the reference points for allocation resource usage. And from that, we connect into that and use our own individual databases in LDAP through a Perl script that we've used in conjunction with other consortia such as WestGrid, which you may have heard of, or Signet. With this Perl script, we basically make use of the CCDB, or Compute Canada database, as we in long form, and our LDAP to basically create account groups based upon resource allocation project identifiers, or RAPIs, as I forgive this Compute Canada terminology. And we assign basically both default and project-based allocations for the course of the year. And those are basically the Fairshare targets that we set. So we use this Identity Manager interface, and with that, we use the XML format and then reference the server and a file that produces this information. We have it configured to do a refresh. And in the simplest of cases, what we have then is a user, which will, for example, be fictitiously me, will belong to two different account groups. We have the membership for those both account groups, and then we can also define a default. And within those account groups, we can assign different Fairshare priority targets. Whether it's for the AAA or the BBB, we can then assign different values. And we're finalizing the configuration of this right now. It's not in production at the moment, but we're finalizing the configuration to make sure we get all the proper information from our local LDAP as well as from the central database. So this is how we define our allocation of resources, basically for all projects. One particular case that we use in terms of the Fairshare is the hierarchical trees. We have certain projects where they actually want to define certain classes internal to their allocation so they can really do a proper balance between different types of workloads, not just on a per user, because these are sets of tens of 20 groups of users. So based upon the type of workload, whether it's for just production Monte Carlo or user analysis, we use the hierarchical tree to split up individual allocations in between individual groups. So in the case here, for the tier 2 operations for the Atlas experiment, what they do is they assign certain amounts for the Canadian use, which is a certain number of Canadian physicists that have dedicated resources effectively. And at the same time, they have different marks where we can set allocations for, as I said, centrally operated Monte Carlo, analysis, and so on. So that way they can have some dynamic control themselves over how they want to set the shares, but at the same time, it fits within the overall envelope that we as a resource provider have given to them. And second of all, we also are looking to use this for specifically individual other projects that may want to target uses within their groups. Now, in terms of resource limit policies, we have the standard ones, of course, as I mentioned, based upon how we organize a queue, so we have memory limitations there. But the one I really want to talk about right now in terms of our implementation is one that we've put in place since the end of February, which is where we use the max PS, or max processor seconds, limitations for each account group. And the reason we do this is as follows. We have, as I mentioned already, the ability to let users run for very extended periods, sometimes up to 30 days, but that can end up sometimes into situations where users, in terms of submitting their jobs to the queue, if we don't have necessarily hard limits that say cap them at their allocation, they can end up blocking resources from other users, which is obviously not, it's good for the user who's blocked, but or the person being blocked is obviously very unhappy. So what we've done is we've used the max PS parameter to define the envelope of time that basically that they're allowed to work with. And through that, basically we can limit the number of outstanding processor seconds with this parameter that can actually be used by a group at any given time. As the job executions go forward, that amount of time actually shrinks and it leaves a buffer of space for them to fit their new workloads in. So it gives them a lot of flexibility over how they want to make use of their resource. If they want to run a single long job, that's fine for them, but they also can get more flexibility if they run shorter jobs to allow them to burst upon over and above their allocation. So for example, our default allocation of say 12 cores on the system represents this amount of max PS seconds. So therefore, as I said, the group can run a single 30-day job on 12 cores, or they can divide it up into smaller chunks for shorter duration, whether it's 30 10-day jobs, 12 5-day jobs with a different number of cores, or if they go down to the extreme of single core, single day running, they can run again to much larger amounts. So we define these with soft limits and hard limits, so that way if the scheduler, if everyone's using the resource, it has some flexibility to go above the soft limit, but we also put in restrictions at the hard limit to let people not abuse the system. Since about February, we've had some good success with this in terms of its utilization to get people there so they're not blocking others. It's involved a little bit of training that we have to do with the users to explain to them why it's to their advantage. So obviously, they run these shorter jobs so they can burst. And also, in the end, of course, allows the scheduler to much more easily fit the workloads in. So this is a work in progress in the sense of, so obviously we make adjustments as we're going along, but we've been pretty happy with it so far. In terms of large system configuration for high throughput, I won't go through in detail, but I'll just mention the fact that we have implemented some of these changes that were discussed already in the previous talk. In our site, for example, we've increased just the maximum number of jobs period since we have a feature that we've been requested by our genomics users. They want to be able to submit up to 16,000 jobs at a time. Okay, fine. So we increased the parameter there. And one of the features that we've enabled is with the new version of the 613 is this asynchronous start in the high throughput. For us, that's been very helpful. Prior to this, we were using, I forget which version of Moab 5, but we were having problems with the server being able to respond to user requests, whether it's show, queue, msub, it would just time out. Yes, you can adjust the timeout parameter so that people don't necessarily get a rejection back right away, but that didn't really solve any of the problem. We needed certain things with the ability to really have quick turnaround in receiving jobs as well as querying the status of things. And by adjusting our configuration for high throughput, we were able to actually cut the actual effective time spent per job being submitted by about 70%. So right now, we're actually getting just about 3.5 jobs per second being able to be submitted through our system right now, whereas it was more on the order of, say, 1 before, which was really problematic. And the perception-wise also to the users was very important in the sense that if they were timing out, they were doing their large submissions. We've reconciled that now by providing increased stability and responsiveness of the system by doing this. So they've been appreciative of this. And one area we kind of noticed this a lot happening is Friday afternoons. Users would go away. They say, I'm going to just kind of script all my submissions for the weekend and go away, and they would submit 10,000 jobs and just leave. This lets them do this, even though we don't encourage it. And we, of course, when we observe these things, we try and take actions to help prevent it. But at least this now keeps the system working well. Now into the customizations part. We've done 2 sets of customizations. One related to memory management, which is kind of specific to our site, and the other one about process and job management. For memory management, within Moab, we have the configuration where we have a default mem value so that the system, when it goes through and it tracks memory usage for a job, if it reaches a certain threshold that we assign based upon the queue parameter or the class parameter, it can then abort the job and kill it. The problem was we found that there was some variability in the time of the system being able to react, where the nodes themselves became unresponsive. And the reason why we became unresponsive, we found, was related to how we worked the systems with our file system, again, GPFS. So what was happening there, since the job necessarily wasn't killed by Moab, we had done some experimentation and testing with the out-of-memory killer, but that was a very, I would say, laborsome and time-consuming approach to preserving the system health. So what we did there was, after doing much tuning, we've kind of abandoned that part. We then tried moving to reducing the pole interval between the scheduler and the resource manager. Now, this might seem contrary to what some advice in terms of a large system. Why would we reduce the RM pole interval? Well, we wanted to try and get quicker feedback from the actual nodes performing the jobs to say, okay, yes, we've hit some boundary condition in terms of memory usage, so we can then trigger the expulsion of the job. Again, that didn't really help. So what we were doing then, as part of all this, the underlying cause was really just by the nature of how we were using the system in terms of a GPFS perspective in the IB layer. So once we hit a certain memory boundary threshold value, we were losing GPFS, jobs were failing, and it was a bit of a mess. So to avoid these job failures and the inability to, say, use the out-of-memory killer and query the status directly through the scheduler resource manager interaction, we went to look for something a little bit more local in terms of how we actually manage the memory usage. So we basically said, okay, let's stay away from communicating with the server. Let's just go to something directly on the worker node itself. For that, we actually then started looking at just the amount of active memory in the system that's being used. And we basically set a threshold, a certain amount less than the physical amount of memory. So we don't use swap in this case. So we set a threshold, which is the total amount of physical memory, and we subtract a certain amount that we want to reserve, say, for the health of the system from a daemon perspective, whether it's GPFS, the IB layer, and so on. So we track then the active memory usage, and then we compare that to that threshold. If it goes above that threshold value, we then tabulate internally which process has consumed the most amount of memory in the system. And as part of that, the communication all comes from the MOM control directly on the worker node. So we don't go back to the server at the very beginning. So we communicate directly on the worker node through MOM control, find out the hierarchy of memory usage, take the one that's the highest memory consumer, and that one then we send back a cancel job right now. And then to alleviate effectively the memory pressure, and therefore basically keeps the file system alive and the system alive from an overall perspective. And we found that has brought about a significant amount of improvement in terms of the stability of our system. We're still dealing with some issues there in terms of how the GPFS part is interacting with it. I can talk with people. I'd welcome any GPFS people in the audience if they want to discuss this afterwards as well. I can give you some of the feedback we've received from IBM in this matter. So that's the one memory management feature that we put in, and that's brought us a lot of stability that wasn't there, say, 3 months ago. And the last one to really mention is the process and job management. Now, for this one, we've observed periodically, and I'm sure pretty much everyone else has in their systems, there's cases where the user processes themselves are launched, and they're dispatched to the nodes, but they're not necessarily done so in a way that's easily traceable and manageable by Torque, for example. And then they can end up actually running beyond the expected or known lifetime of the job within the system. So a straight process, basically, something that can't be tracked by PBS-MOM. Now, there's various scripts that people have done. We've kind of adapted ours that we did for the memory management side, where we actually search for those straight processes using tools directly on the worker node. Now, as I said, the sources of these things can be a variety of situations, whether people doing things that we discourage them and tell them not to, such as using MPI run or our MPI run R shell. PBS mom might die unexpectedly for various reasons, or they just might spawn their jobs just using regular shell options once they get their node list. And again, those necessarily don't make it easy to track. So for that, we actually identify all the stray processes directly again on the worker node without going back to the server. So we get a snapshot of all the processes, again, looking at through the output from mom control. We get the list of the processes, the heads of the process trees, and the full set of children processes that are running on the nodes that can be attributed to the node from a torque perspective. As part of the second step, then, we look at the full list of all user processes on nodes, and we look for any mismatches. If a process doesn't exist in that first list that comes back from mom-controlled hierarchy that we identify, we consider that a stray process, and we can then do a cleanup, either a manual cleanup like we do currently, or an automatic action that we look to do in the future. So right now we do this on a daily basis. Depending upon what's happening on the system, we've had to do a little bit more manual work, but we're looking to update this in the future for more automatic action. So not necessarily a scaling issue, but in terms of if you have thousands of nodes, and if you have people doing leaving stray processes on those thousands of nodes, you need something that lets you do that cleanup in an efficient way. And this is one way that we found to do it. I won't touch too much on this, but just to highlight some of the things that obviously I'm interested in hearing what's coming out or what's out now with Moab 7 and the viewpoint and so on. But what we've done as part of our overall operations to simplify how we interpret things. We get lots of log information from syslog, from the torque logs, Moab logs, and so on. And what we've done is we've taken kind of a snapshot of some of the bits of information that come from a variety of sources, and we just kind of do a visual representation to give our people when we come in the morning, okay, what has happened overnight, rather than reading through the tons of email reports. I just want a quick visualization of what the problems are. Right now, one that we are experimenting with is just using some jQuery libraries and AJAX calls that basically pull information using PHP and Python from these logs to generate some visualization of the system as a whole. Now, this is just an experimentation, so we're going to see how this goes. Obviously, we're interested in leveraging other tools that might be out there, whether it's directly from Adaptive or from others. But this is one thing that we've kind of started building to get a full picture view of how the system is behaving, not just from the scheduler, but also from things like our IB layer, as well as our memory behavior as well. So our future plans, just in terms of the scheduling, policy, and implementation, certainly we want to evolve the system and make improvements. So we want to have a continuous evaluation of how things are working. One thing that we're going to evaluate doing is moving from partition-based queues or classes to time-based, just to make it a little bit easier for users. Not that it's a necessary issue now. We want to look at other fine-tunings on how the Moab Torque communication process is happening. Sometimes we've seen the process communication fail, so one of the parameters I think that's relatively newly available is this RM fail count. So we want to try out and see if that is applicable for us, as well as the TCP tunings between the clients, meaning the PBS moms, and the servers. And we also have a shared memory system that we want to incorporate in our system, so we're obviously interested in how we work with the shared memory side of things within Moab. Depending on the scaling features, if we see if in Moab 7, obviously, if we get very solid and very responsive interaction with people, we may not need it. But what we've seen other places do is they do some sort of caching of the output of show queue. That may or may not be necessary, but we'll consider it if we find it required. And of course, we also want to train our users in the proper use of the system, not exclusively in things like job arrays that I mentioned in the slides, but just more generally about using the system. And we also want to reinstate our previous setup we had for high availability for Moab and Torque. All these changes to the scheduler we want to take with the viewpoint that our system is going to be expanding, as I talked about already, later this year. We're looking to have, by fall, implemented an expansion of our system to about roughly double our number of nodes and close to 30,000 cores in our system. We're going to be adding some GPUs into the mix and also increasing our storage. So while it's not directly related to how we implement things in the scheduler, looking at how we maybe want to possibly enable certain clients to access the HSM layer, we may or may want to do or investigate. So my last slide, hopefully I've outlined in very rapid fashion without too much duplication with the previous presentations about some of the things that we do in terms of how we allocate our resources, manage them, limit the usability of it in terms of preventing abuses, but also at the same time trying to maximize throughput for people and responsiveness of the system. So from my perspective, knowing how other people are doing things and knowing from the attending here this week is very important, since we were looking to really evaluate in a continual fashion how we move forward. So with that, I'd like to just conclude. I certainly look forward to the remainder of the sessions this week, and I'd like to obviously thank my team back in McGill and the others at the consortia that we work with elsewhere in Canada, and of course Adaptive for their help with things. And even though the weather's not particularly like this outside right now, thanks for your attention, as opposed to wanting to make this a ski conference and leave some of the presentations. So thanks for your time.